So here in lecture 11.5, we're going to look at non-uniform grid costs. So this is another feature addition to the basic maze router method, but maybe a little subtle one. One of the things that's been true in all of the grids that I've shown you so far is that the cost of traversing one single cell was always 1. Is that a requirement? Is that a critical foundational part of the maze router method? No, I'm free to put any cost value in any cell I like. Why would I do that? And what's interesting is that I could actually seed the routing grid with costs and drive the shapes, the geometry of the nets to do things that I like. I could put high cost values in a region of the grid representing some part of the chip that I would prefer the nets as they are routed avoid. I could put low cost values in other parts of the grid representing the chip surface and preferentially sort of drive the nets to use those low cost regions. It is an amazingly flexible method. It is actually the way all real industrial routers do their business, and it's a surprisingly simple feature add to the basic maze router methodology. So let's go look at what cool things we can do with non-uniform costs in our maze routing grids.
So the next feature that we're going to add to our basic maze routing core is to allow the individual squares in the grid to cost something other than 1 to use as a part of a path. So in the original way we specified this problem, each cell in the grid costs the same to cross it. So more or less that means everything costs 1. We say that this is the unit cost grid case or uniform unit cost grid case. Is this necessary? No. Now, given a source and a target, and again, I've got my 6x6 grid shown here with a source in the upper left and a target in the lower right, I'm going to allow you to have different costs for each cell. So it will no longer be the case that when we do the expansion process to sort of search for a path, when I say find all the cells that are paths of length 6, find all the cells that are paths of length 7, length is not really what we're going to be looking at anymore. We're going to say, oh, let's find the cells that are the cheapest to expand next, and we'll figure out what they cost, and what they cost will be based on the cost of the path to find them and the cost of the grid that is used. So we need to find some different language for describing how this expansion process works. The process is going to be basically the same. The way we describe it is going to get a little bit different. What we're going to move toward is finding the minimum cost path that connects the source to the target. So what are we going to do? We're going to put some new cost items in the grid. So in my grid, a great big set of orange squares has appeared. 2 cells high, 4 cells wide, and they all have 3s in them. So it does not cost 1 to add this cell to your path. It now costs 3 to add this cell to your path. So you can think of this as being something that's expensive, and we'd sort of like the path not to use it if it doesn't have to. Right? That's what you do with a cost. And so just to be clear, the shaded cells, the orange cells, cost 3, and the unshaded cells, the white cells, cost 1. It's just easier not to put all the 1s in the grid. It just makes it visually sort of cluttered. So a white cell costs 1. Something that doesn't cost 1, I'm going to label it for you in some special way. So we need to define a new metric for the quality of our paths, and that's just the path cost. And that's just the sum over all the cells in the path of the cost of each cell. It's really quite simple. Take all the cells you use in your path, add up the costs. So here on the left, I've got my 6x6 grid again, with a 2x4 element of 3s, the high cost things in it. And I've got a sort of a straight, simple path from the source in the upper left to the target in the lower right. It's just an L shape. 4 cells in the vertical arm, north to south, 4 cells in the horizontal arm, west to east. What does this path cost, this bright red path cost? And the answer is, well, the source cell costs 1, the next cell costs a 3, the next cell costs a 3, the corner cell costs a 1, and then the other cells that get you to the target cost a 1. 1 plus 3 plus 3 plus 1 plus 1 plus 1 plus 1, that's 11. This path costs 11. So the short, straight path costs 11. What's another path you might consider? Well, how about this path? This path avoids the high cost region. This path first goes to the west by 1 cell, then goes south 4 cells, then goes east 5 cells to make a connection to the target. It doesn't use any of the cells that cost 3. What does this path cost? And the answer is, well, every cell on it costs 1. The source costs 1. The corner at the top left costs 1. The path down costs 1. The corner at the bottom left costs 1, and then all the cells on the path to the target cost 1. You add them up, there's 11 of them. I'm sorry, there's 9 of them. This path costs 9. Oh, look, something interesting happened. The path on the left is short, but the path on the left is expensive. Why is it expensive? Because it used this high-cost region, and maybe we don't like that. The path on the right is long. The path on the right is cheap. Perhaps we prefer the path on the right unless the wire is in trouble. You know, it's got blockages all over the place and the wire really urgently needs to use that piece of space. Then okay, I'll put the wire there, even then I'll make it more expensive. But if you can, please find a path that doesn't use those high-cost cells. This is an incredible important way that you can change the fabric of the routing grid in ways that will encourage nets to take paths that you like. This is a big deal. This is very important. This is a really vital feature of all real routers. You use costs to encourage wires to take shapes that you prefer. So you can make the router avoid a congested area. Suppose you can do some analysis that says some regions of the chip are going to have way more wires that want to put their paths there than there is space to put paths there. You might put some big cost values in the grid so that the early wires you route don't just go there, and you leave enough space for the later wires to get through when you need it. You can make different layers have different costs to use. You can make different vias have different expense to use. You can make different directions of expansion more expensive. You know, you might decide that some layer you want mostly vertical wires or some layer you want mostly horizontal wires. We'll talk about that later too. But it does have some profound impacts on the search process of expanding out. So it's no longer the case that we're going to say, find all the paths that are find all the cells that are on paths of length 6, and then find all the cells that are on paths of length 7, then find all the cells that are on paths of length 8. No, that's the way you start it, but now what we're going to say is, find the cells that are labeled, whose neighbors are not labeled. Figure out what it costs to reach the cells that are not labeled. When you do that, then find the new cells that are not labeled, who have neighbors that are, find the new cells who are labeled with a cost, who have neighbors that are not labeled with a cost. So you get the same expansion of wavefronts with costs, but you're not really just searching all the paths of length k and then all the paths of length k plus 1. And we get some technical questions. You know, what does it cost to reach one of the non-unit cells? What does it cost to put a via on a non-unit cell? So let's just go look at the mechanics. Here's our friend, the grid, 6x6, source in the upper left, target in the lower right, 2x4 region of high-cost cells that cost 3 in the middle. We can still start with the same language, right? You know, the source is going to cost 1, and we're going to find all the cells that are sort of, you know, 1 unit away in distance. We're going to find all the neighbors of the source. But then we're going to have to find some different language for labeling things. For the way this sort of works. So, you know, when we start, the source gets a cost of 1. That makes sense. And then we're going to look at the neighbors of the source that are not labeled with a cost value and say, what does it cost to get there? And those are all the cells that are just next to it, you know, 1 cell away. So to go to the west, that costs 2, 1 plus 1. To go to the north, that costs 2, 1 plus 1. To go to the east, that costs 2, 1 plus 1. But to go to the south, that costs 4. Right, that costs 4 because that's 1 plus 3. So I'm just going to put an arrow that says that cell costs 4 because you expanded the source, which cost 1, using the cell, which costs 3. Right, so far this is all good, and you know, there's nothing interesting here, and you wonder why I'm belaboring this point. But now, let's look at the cell that's to the south and the east of the source cell. We have not seen this situation before. In all of the previous examples that we did, both of the neighbors of this red highlighted cell would have had the same number on them. They don't. The cell to the north costs 2. That's the minimum cost path to find it, and I could expand to the south to reach this cell. I could also use the cell to the west that costs 4, and I could expand to the east. What's the right answer? So just to put this in words, what is the cell's path cost to be reached? The highlighted red cell that is to the south and the east of the source cell, that is orange, that costs 3. Is it 2 plus 3 equals 5 because I'm coming from the north? Or is it 4 plus 3 equals 7 because I'm coming from the west? And the answer is, it costs 5. And it's important that you always, always want to label cells with the minimum path cost to reach that cell, because otherwise this whole idea doesn't work. I want to be able to search the grid to find paths of minimum path cost, where that just means when you add up all the costs of the cells on the physical path, I get the path with the smallest number for the path cost. So the right answer is the cheapest way to get to cell the red highlighted cell is 5. It's to go east through the cell that costs 2, and then to go south with the cell that costs 5. We're going to have to get the mechanics of this algorithm right so that it always does the right thing. Next, what if I have a via scenario? So I've got basically the same scenario from the previous slide where the source expanded, and there were some 2s to the west and the north and the east, and a 4 to the south, and then there was some 3s and a diamond around that, but this 5 to the south and the east of the source. And suppose that 5, the big red square, wants to expand to layer 2. So I've got another 6 by 6 grid on the right side here. And it's got a great big area of high cost that's 2 cells wide and 4 cells high, sort of on the left of this. And all those cells are real expensive. They cost 6. And one of the things that's true is that that cell that's red on the left on layer 1 that wants to put a via to go to layer 2, that's on top of a high cost region. If you put a via in and you go to layer 2, that cell costs 6. So I have a question here. What does it cost to get to that cell? Okay, what does it cost to get to the same cell, 3 rows down from the top, 3 columns over from the left in layer 2, if we expand from the cell that costs 5 in layer 1? And the answer is, I need to know what the via costs. So I've got it highlighted here. The via costs 20. So what does it cost to get to that cell labeled 6, because the cost of that cell is 6 in the layer 2 grid? And the answer is it costs 31. Why? The cell you started with costs a 5. That was the path cost to get to that cell on layer 1. It costs 20 to put the via there. Why? Because I told you that it costs 20 and vias are expensive. The via gets you to layer 2. What does it cost to use the cell that you land on in layer 2? Answer, 6. Why? Because I said so. That cell is expensive for some appropriate reason. What does it cost to get to that cell on layer 2? 5 plus 20 plus 6, 11 plus 20, 31. It costs 31 to use that cell. All right? So what do? We're going to show you some mechanics to search these grids, parallel grids with complicated costs and complicated via costs to find the minimum cost path. It's going to turn out to be a surprisingly simple and elegant algorithm. So here's a kind of a midpoint summary. What do we know? We know about this grid-based expansion one net at a time thing for maze routing, and that we can use costs in the grid to get different effects. And we know we can deal with complicated physical scenarios like multiple wiring layers and multi-point nets. But there's a bunch of stuff we don't know, and we just started to get to the point where not knowing it was a problem. I don't know real implementation strategies. I don't really know how I build this thing. I don't know what the real data structures are. I don't know how cells get touched during the search. That's the big thing. How do I expand cells? How do I reach cells? It was good and easy when I said, find all the paths of length 7. Good. Find all the paths of length 8. They're 1 cell away. When these cost values start happening, you got to be a little more careful. And there's some subtle interactions between the cost strategy and the search strategy, and surprisingly enough, there are some cost mechanics that we can put in that actually break the way the search works, and even though they break it, we do it anyway because it's actually really important to the physical stuff we're trying to accomplish with the router. So we've done sort of a discussion of the features that we want in routing from the point of view of a user, somebody trying to wire nets. Next, I got to look at the real implementation mechanics, and so we're going to put our computer science hats on, and we're going to say, hey, algorithms, data structures, how do we actually make this stuff work? Let's go look at that next.